In this video, I'll talk about the rate determining step or rate limiting step in a complex reaction mechanism. So first, these two terms, rate determining step and rate limiting step, are referring to the same thing. And then I'm going to give you an example about this rate determining or rate limiting step. So let's say there are a lot of people in the theater watching a movie. After the movie, people are walking out. And then this theater is designed in a really weird way. So the audience will have to pass through the first corridor here, so this one, really wide, and then this one, and then this one. So 3 corridors, wide, narrow, medium. And then we can see that it's possible for a lot of people to pass through this first wide corridor at the same time. Therefore, on average, people can go through this fairly fast. But now it becomes narrower here, and fewer people can pass through this corridor, within the same time period. And finally, the last one is the narrowest. It allows only one person to pass through at a time. So my question is this. Let's say 100 people can pass through this corridor per minute. 10 people can pass through this second corridor per minute. 1 person can pass through this last narrowest corridor per minute. So 100 people per minute, 10 people per minute, and then 1 person per minute. So overall, if we observe at this exit, overall, how fast can these people walk out of this exit? So obviously you can tell, well, it's going to be just 1 person per minute because this corridor is the narrowest corridor. This is the rate determining corridor or the rate limiting corridor. So what if I swap these 2 corridors? Or maybe I put this one here. So it does not matter. All right. So again, all people will have to pass 3 corridors. The narrowest one is always the rate determining one. Now I'm going to give you another example, this time a chemical reaction. But this time, this is the energy diagram of a reaction. The left-hand side, we have reactants. So this is the energy of the reactants. This is the energy of the products. So over here, we have the first energy barrier, a small one. And the reactants can overcome the first small energy barrier to become the intermediate in the middle. The intermediate can overcome the second, much larger energy barrier to form the product. If we look at this first energy barrier and the second energy barrier, again, the first barrier is small, so the reaction rate is higher than the rate of the second step. The second step is slower because of the much larger energy barrier. And then we say the slower step is the rate determining step, RDS, or rate limiting step. All right? So it doesn't matter how fast the first step, this reactants can be converted to the intermediate. Because the second step is so slow, it takes so long for the intermediate to be converted to the product. The overall reaction rate, the overall rate of the production is limited by the second slower step. Now I'm going to show you 2 practice problems. The first one. Let's say we're looking at a complex reaction mechanism from A to B and then from B to C. So overall, it's from A to C. This is the overall reaction mechanism that consists of 2 steps. A is converted to B first, and then B is converted to C. So first, from A to B, the rate constant is 10 per second. And then the reaction rate constant from B to C is 1000 per second. So which step is the rate limiting step? Well, this is 10, this is 1000, so we can tell this one is slower. The slower step is the rate limiting step. And then what's the apparent observed rate constant of this mechanism from A to B and then B to C? Well, it's going to be 10 per second because, again, this step is the slowest step. Therefore, this overall reaction rate from A to C, or apparent reaction rate from A to C, or observed rate constant from A to C, is going to be the slowest, 10 per second. All right, so the answer is here. From A to B, that's the rate limiting step. Again, the slower step, or the slowest step. Okay? The apparent rate constant from A to C is going to be, again, just 10 per second. All right? So you can imagine this is also a theater scenario. So from A to B, this is my first corridor. We allow 10 people to pass through per second. And the second corridor allows 1,000 people to pass through per second. But overall, okay, the rate of people, passing through both corridors is going to be limited by this one. So overall, it's going to be 10 people per second. The second practice problem is here. Now this time I'm going to give you the reaction energy barrier. For A to B is 10 kJ per mole. The reaction energy barrier from B to C is 1000 kJ per mole. And then which step is more likely the rate limiting step? All right, so this is the question. We just compare these two energy barriers. This is a small energy barrier, therefore from A to B it's going to be fast. This is a large energy barrier, therefore from B to C it's going to be really slow. All right? Why? Because, again, the reaction rate constant, K, is equal to A, the pre-exponential factor A, times the exponential function. And what's the exponential function? It's e to the power of negative energy barrier divided by RT. So if you have a larger barrier, you have a smaller K. Smaller barrier, you have a larger K. All right? So that's the reason. From A to B, you have a smaller energy barrier. So from A to B, this is fast. From B to C, the energy barrier is huge. Therefore, the reaction rate constant from B to C is very small. It's negligible. Okay, and then from B to C is the rate limiting step. Now I'm going to give you a numerical example here. Just assume RT is 2.5 kJ per mole. R is the gas constant, T, let's say room temperature. And then if you multiply R and T, you're going to get roughly 2.5 kJ per mole. All right, and then let's look at the Arrhenius equation. So the Arrhenius equation is K equals the exponential function, A, this is the pre-exponential factor, times e to the power of negative energy barrier E sub A over RT. And make sure we put this negative E sub A over RT in the superscript. Okay, so what's this equation? This is the famous Arrhenius equation. So again, if we look at this term is much smaller when you have a large energy barrier. So E sub A stands for activation energy. And activation energy is the same thing as a reaction barrier or reaction energy barrier. So we can plug in some numbers here. Let's say room temperature RT is 2.5 kJ per mole. And then let's calculate the value of this exponential function. If the barrier is 10 kJ per mole, this exponential function is e to the power of negative 10 over 2.5. So this is e to the power of negative 4. It's roughly 0.02. All right, 0.02. Now, what about a larger barrier, 1000 kJ per mole? We plug in this number, negative reaction energy barrier over RT. So over here, negative activation energy or energy barrier over RT is what? 0.00000. You have to say 174 zeros before you can say this number 2. So look at this exponential function. All right, it has such a small value because of such a large energy barrier or activation energy. Again, activation energy and reaction barrier and reaction energy barrier are the same thing in chemical kinetics. Alright, so the answer is simple. B to C has a much larger energy barrier and this is really, really slow. So B to C is very likely the rate limiting step.